Could be. It's a very small chapter. It's a very easy chapter also. So we'll be done today.
Is it like numericals heavy or theory heavy?
Oh, this is your first chapter of inorganic chemistry, right? Okay. So your whole chemistry syllabus is divided in three different things. You have physical chemistry, you have organic, and then there is inorganic chemistry. So physical chemistry has everything to do with processes and reactions and the physics behind it, you know, the energy changes. So you have your thermodynamics, states of matter, like your gas laws, what happens to the pressure and temperature when, let's say, I evaporate something, or if I do a certain reaction, or if I mix two different types of gases. All of that comes under physical chemistry. Going deeper, like in grade 12, we're going to have, structure of solids, like solid state, solutions, like what you did in chapter 1, stoichiometry, reaction mechanisms, things like that, all of that in under physical chemistry. And then you have organic and inorganic chemistry, which is all about materials and matter. Like you're going to pick each and every element and study about it. Organic, you guys have already had a taste of it. So we've done basics of organic chemistry, and most of you have started hydrocarbons also. So you'll pick each class of compounds. You're going to take alkanes, study what are their physical chemical properties are like. You'll take alkenes and you'll take alkynes, and then you'll take haloalkanes, you'll take alcohols, you'll take acids, like pick each one and study about them. Inorganic mein, you're going to study the whole periodic table group wise or block wise. So you're going to study about S block elements separately, then group 13, group 14, group 15, like all of each of the P block elements. And then you have a whole chapter on D block elements and F block elements. And when I say study about these materials, it's just getting to know them. You know, what do they look like? What do they behave? Like your physical properties, color, taste, density, boiling point, melting point, and their chemical properties. How do they behave with other substances? Like if I take sodium or potassium, like any S block metal, if I put it in water, what is going to happen? If I burn it in air, what is going to happen? If I put it in an acid, what will happen? If I put it in a base, what will happen? Stuff like that. So all these inorganic chemistry chapters, in grade 11, you have hydrogen, you have S block elements, and you have P block elements. Like P block, maybe you just have group 13 and 14, that's it. 15, 16, 17, you have it in grade 12. So they're all structured in the exact same way. In fact, organic is also structured in a very similar way, minor differences between both. So first you'll have an introduction where you look at group trends, oxidation state, top to bottom, what is the trend, ionization enthalpy, what is the trend, boiling point, melting point, like general, what are the group trends like. Then you'll have a whole section about the physical properties. You'll have a whole section about the chemical properties. Apart from that, in case there's any special notes about them, like diagonal relationship, like you already had a little bit of it in periodic classification, that sort of any special notes about it, that will be added on in the end. Even organic chemistry, alkanes, alkenes, alkynes, instead of group trends, in organic you have nomenclature and structure, and then you have the physical properties, chemical properties, and that's it. Uses and any special compounds, if there's any, that's it. Okay. So inorganic chemistry, organic, at least if you know the mechanism, there's like some sort of a logic that you use. Plus psi effect, agar resonance hoga, to how is the reaction affected? Like you can use some sort of a logic there. Inorganic chemistry is going to be mainly memory based. It's just information. Some things like trends, oh, if there's hydrogen bonding, this is how these things change. Like you can apply logic to it, but I would say it's like 60-70% memory, and then remaining 40%, some sort of, you can deduce it. using logic. Physical chemistry is completely, it's going to be so much like physics. You have a set of formulae and you have to apply them. Okay, so this is kind of how your whole chemistry ka syllabus is divided. So your study also will be like, you'll have to change your method of study depending on which chapter you're studying. So in organic may a lot of memory based devices, constant revision, like make notes, keep writing. Physical and organic chemistry ke liye, the more number of questions you solve, the better you'll get at it, because that's where a lot of your exposure basically happens. Okay. So you guys ready? Should we start the chapter now? Any more questions you guys have on what it's going to be like?
The name is only hydrogen, right?
Yeah, name is hydrogen. We're going to be studying all about hydrogen. And why are we studying hydrogen separately? Only single element will be evident. Like, that's the first thing we're going to tackle in this chapter. Okay, so you guys have known hydrogen already. You guys have come across hydrogen, the element. What all do you know about it? Like, if I say we're talking about hydrogen, what's like the first thing that comes to your mind about it?
It's the first element in the periodic table.
Absolutely. So
And it has one electron only.
Only one electron. Hydrogen symbol is H. Yes, one electron. What is the atomic number, atomic mass?
One.
Everything is
One.
atomic number.
In the first group of the first period.
Yes, absolutely.
And the position is a bit controversial
There you go.
in the modern periodic table.
Yes. What is the electronic configuration of hydrogen?
1s.
1s1.
I think 1s1.
Yes, the single electron it has goes in the very first shell. So as Rishit said, the position is anomalous in the periodic table. Why is that?
Because its properties match with alkali metals as well as halogens.
Absolutely. So let's go a little deeper. So that is the main confusion when it comes to hydrogen. Okay. So what are the properties that match up with alkali metals?
The one valency.
So with alkali metals, yes, so electronic configuration is of the form NS1, valency is 1. Valency 1 matlab halogens bhi valency is 1, right? So you need to be a little more specific when it comes to
Valency is +1.
Yes, electronic configuration matches with alkali metals, shows oxidation state, like it forms H plus like alkali metals. What else?
It pairs up with halogens the way alkali metals do.
Absolutely, not just halogens, but it also forms like hydrogen forms halides, just like alkali metals, like NaCl, PCl, जैसे HCl होता है. Also forms oxides and sulfides.
Do we write this down?
Yeah, absolutely. Yes. Make notes. So here you can write similarities with alkali metals, and then we'll discuss similarities with halogens. Yeah. So all of these, like these three behaviors, show its similarity with alkali metals. Okay. Now, what about similarities with halogens? Because that's where the debate is, right? Like, should we put it with alkali metals or should we put it with halogens?
Valency is -1.
Correct. So basically, hydrogen is one electron short of noble gas configurations like halogens. Yeah, it can show -1 valency also. Other way of putting it. which means hydrogen also forms H minus and covalent bonds, just like halogens. Okay. What other similarities with halogens? Think of halogens, like you have fluorine, chlorine, bromine, iodine. How do they exist in nature normally?
They exist in gaseous state.
Gaseous state.
Gaseous state. And what is the formula, let's say, for chlorine gas?
They're diatomic. Diatomic.
Diatomic.
Correct. And what does hydrogen exist as, like natural state mein?
H2.
Right.
H2.
That's another similarity. So just like halogens, this is a non-metal, exists as a diatomic gas or gaseous diatomic molecules. H2, similar to Cl2, F2 and all of that. And another similarity is, again, this is something that you have to look at the values. Just like, so alkali metals, what can you say about the ionization enthalpy? Like, does it trend high or does it trend low?
High.
How high? Kaveri, what is ionization enthalpy?
From left to right?
No, generally for alkali metals, what is their characteristic for ionization enthalpy? Is it?
I thought you were from left to right. I was saying it increases. Yeah, but for metals, it's less.
Yeah, usually ionization enthalpy of alkali metals is pretty low. And for halogens, it is pretty high. As you said, it trends high, right? So if you look at the numerical value for hydrogen's ionization enthalpy, it is pretty high, just like halogens. Characteristic, it is characterized by a very high ionization enthalpy. Yeah, so you've got similarities with alkali metals, you've got similarities with halogens. Actually, I'll show you guys the value for ionization enthalpy. So you guys can note down these points in the meantime. Yeah, start making your notes and then we'll discuss the next part. Yes, let me know when you're done here, yeah? Then look at this. No, all of you are done. Okay, Sanat and Adit, okay. Okay. Uh, so you can see this graph here. So hydrogen is a little less than like 15. So 1500, like these are into 10 square, you can think of it as. You can see all the alkali metals are down here. You have lithium, sodium, potassium, rubidium, like one of the lowest.
These are ionization enthalpies,
Yeah.
right?
Yes. And all the P block, yellow ones are P block. All the halogens are around 1500. Like fluorine has pretty high, but after that, chlorine is slightly less than 15. Bromine is also a little less than 15. Iodine is also somewhere over here, right? So hydrogen is trending more similarly with the halogens as opposed to alkali metals, which are like way low over here. Yeah, so that way you can see in terms of ionization enthalpy, in terms of ionization and all that, hydrogen is a lot more similar to halogens than the alkali metals.
Ma'am, the red dot represents S block, but what does many red dots mean? Like, I think hydrogen has two of them or one.
Hydrogen is NS1, no? So this is hydrogen over here.
So one dot means only one S block.
No, all the red dot represents, it means that that's a S block element. So all the yellow dots, these are the P block elements. The blue ones are D block elements and the green ones are F block elements. So you can see like all the D block, F block ionization is kind of, F block especially, they're all very, very similar to each other. We'll come across that when you guys study F block. But yeah. Yeah. But abhi ke liye focus on the S block ones. Hydrogen, similar to P block, more similar to P block than your S block elements. So that's another argument for, stating that, hey, hydrogen is more similar to halogens, so wahan pe rakhna chahiye. So that's the whole debate. Yeah.
Why was helium a part of the S block
Because 1 is 2.
in the chart?
Configuration. No, so it is 1 is 2. That's why. Okay. Sanat, is your hand raised from the previous thing, or do you have a question?
Oh yeah, I was just like to mark that I'm done.
Okay. Okay. So that's a whole debate, and excuse me. Sorry. Yeah. So the whole answer to this debate is if people are not able to place it with alkali metals or with halogens, yeah, the compromise that people have arrived at is to keep it in its own category, like keep hydrogen separately. And that's why hydrogen alone is a separate chapter, and rest of the chapters are all group wise, block wise. Yeah. So hydrogen is a very special element. Okay. So that's the introduction, what is hydrogen, its electronic configuration properties and all that. So the first thing we discuss for every element is the occurrence. Where and how do you find hydrogen in nature?
I don't think it's found in its elemental state, right?
Of course, it's found in elemental state.
It
Actually,
is?
it'll be a little more specific. What do you mean it's not found in elemental state?
Like how we find oxygen gas and all.
In the atmosphere, yeah, hydrogen, you don't
Yeah.
really find it a lot in the atmosphere in elemental state.
It's like less than 1%, I think, right?
Yeah, definitely. It's really, really trace, yes. You need to create hydrogen in the elemental state to get it like that. So on Earth, yes, it is not. Hydrogen is the most abundant gas in the universe, followed closely
Because
by
it's found in space.
in space. In space, where the space is empty, right? Vacuum.
Uh, I've read this somewhere. I can't remember. I will get back to you.
Yes.
Maybe not hydrogen individual, but wouldn't it be found in water?
Oh yeah, combined state, it is pretty abundant on the Earth's crust. Let's do it one by one. Okay, first we'll talk about elemental hydrogen, and then we'll talk about in combined state where you find it. So I'm saying elemental hydrogen is the most abundant element in the whole universe. Why is that so? Where do you find it in the universe?
Other planets?
Planets, okay, not all of them. Like just like Earth, Mars also is more iron oxide and carbon dioxide, not hydrogen.
Yeah.
Venus also is like heavy gases like sulfur dioxide and all.
Jupiter.
Jupiter.
Jupiter, yes. So when it comes to planets, in the solar system specifically, because outside the solar system, planets, I at least I don't have so much knowledge of that, but Jupiter and Saturn, the gas giants, have a lot of hydrogen. Apart from that, again, I'm talking about the whole universe, right? This is not sufficient to make it like the most abundant element in the universe. So where else do you find hydrogen?
Is it a very obvious answer that we are missing, or is it a
Yes,
bit hard?
very
In
obvious.
stars.
In
In stars?
Stars. Stars are mostly hydrogen and helium, followed by all the other elements that are made in stars. Yeah. So
Then
stars,
wouldn't sun also come?
absolutely. Sun is a star.
Yeah.
Yeah. So solar atmosphere, Jupiter. So in the solar system, Jupiter, Saturn, and the solar atmosphere are like major contributors for hydrogen. In general, in the whole universe, you find it in stars. In fact, you can see stars because of hydrogen, like hydrogen fusing, forming, and then fusing into helium gives off that light and all of that energy. Okay. So elemental hydrogen.
How do we know? Like sun, we can tell because it's close by, but the other stars could be made of something else, and we wouldn't know. We've never actually been there. They could have like an entirely different set of elements.
So you identify what substances are there, not by chemical analysis. You do spectroscopic studies, like you analyze what sort of energy stars are giving off, and then what is the possibility that okay, how do we get this much amount of energy and these specific radiation, like what all processes can give that off, and then you do spectroscopic studies, like the light from stars, you make it pass through a spectroscope, spectrometers, see what sort of spectrum you're getting, and based on that you identify, okay, what all elements are present in that.
So that's exactly my point. Like you're comparing it to like the elements we have, right? But what if they have like an entirely different element that has like the same radiation as hydrogen, but is not hydrogen? Like, or there's like some other specific condition over there that makes another element act like hydrogen a little bit.
Well, based on the laws of like physics that we have so far, all of the results fit. And if the laws of physics are completely different in a different part of the universe, then our whole science, our whole methods are itself wrong. So, but whatever theoretically, whatever our assumptions are, and if you do the experiments practically, the results are matching. So you can take that to be the conclusion. Like you can go with that. Yeah. So that way,
Ma'am,
being very proven, like accepted. Yeah. Okay. Yeah, Rishad.
So when you say element in the universe, so is it like I missed out maybe, but did you say like it is in the elemental state
Yeah.
or
Elemental
okay?
state, and in general, like if you count how many hydrogen atoms are there, be it natural or combined state, in the whole universe, hydrogen gets like the first prize, like that. And in the elemental state, if you were to find, yeah, like it is the most abundant. It is present in all the stars plus some gas giants like Jupiter and Saturn. Even other planets have it in trace quantities, but these are like the major contributors to where it is. Jupiter, Saturn, specifically in the solar system. Stars in general, like rest of the universe. Now, coming to Earth, elemental hydrogen, you don't really find it, not so much on Earth. What is the reason why we have oxygen, nitrogen, all these other gases, but we can't find hydrogen in our atmosphere, even though it's like a pretty common gas? It's the first element that's formed.
Is it because it's like too reactive that it just reacts with other elements?
No, reactivity is not a problem. Like oxygen is also like it's the second most electronegative thing, right? Yet we have oxygen gas, like elemental state. So you guys
Could
have,
you repeat?
so hydrogen, even though it's the most abundant element in the universe, you don't really find so much of it on the Earth's atmosphere. Like in the atmosphere, it's not among these gases. What is the reason for that?
Because like it exists in other forms. Also, if there was a lot of hydrogen, fires would never go out because it's supposed to.
Then the Earth would be a completely different place. That's more like a consequence of it. But what is the reason that it's not there in the first place? It's not like we're consciously being like, oh, this is a different gas. It's a very reactive gas, so let's not put it in the atmosphere. It's not like that. No? It's just naturally not present. Why?
I have a theory. I'm not sure if it's correct.
Mm-hmm.
So it acts both as like a halogen and an alkali metal. So all the other gases that are like extremely reactive, hydrogen can easily like pair up with them, which is why you don't find it like so much in the Earth's atmosphere.
No, the activity is not a problem with hydrogen. Like if you give it enough energy, like sure, but it's not spontaneously reactive.
No, not hydrogen being reactive. Like other elements being like reactive, but hydrogen being something that can help them like stabilize.
No, that's not the reason why it's not there. It hasn't reacted off with everything else. That's not the reason.
Is it related to chemical property or physical properties?
That's a good question, Kaveri. Before I answer your question, Adit, you raised your hand. Did you have any answer?
I just wanted to ask, like, what factor are we talking about? Like, if it's not in the case of reactivity, then what are the factors?
Okay, so that hint I'll give you. It is related to the physical property only, Kaveri, not chemical property.
So maybe it's like I don't know. I'm just guessing like the weight, like it's light. So
Very good. That is the answer, because it is extremely light. It is the lightest gas, like atomic mass 1, like dihydrogen matlab atomic mass will be 2. You guys have done gravitation in your physics class, right?
Yes,
Have you guys completed the chapter or is it still ongoing?
it's still ongoing.
Ongoing, okay. Have you guys come across this word called escape velocity? You guys done that concept?
Oh,
No?
No, but I know what it is.
Oh, okay. All right. So Ritu, what is escape velocity?
I read it like on some space thing that was coming on the news, which is basically like the amount it needs to escape from the Earth's velocity. I mean, from the Earth's gravitational pull.
Correct. So do you know like why we are all existing on Earth, like even though Earth is like within space? Because Earth is pulling us with its gravitational force, right? Have you guys wondered why Earth has atmosphere but Moon does not have an atmosphere? Why is Moon like a cold, dry rock?
Because it doesn't have enough gravitational pull to hold an atmosphere around it.
Yes, absolutely. So it like the Moon is really small that it doesn't have enough gravitational force to hold any number of like gases or gas particles around it. That's like the result is that the Moon does not have like a sheet of air or any sort of gas, so no atmosphere. Earth has enough gravitational pull to hold like the heavier gases. That's why you have nitrogen, oxygen, carbon dioxide, oxides of like nitrogen and sulfur, like sulfur dioxide, nitrogen dioxide, pentoxide, all of that. And you have like some of the noble gases. But in the Earth's atmosphere, you don't find hydrogen, you don't find helium, because they like these gas molecules are always moving around, right? So as they move, they are not affected by the Earth's gravitational force. They're light enough that if they end up going upwards, they'll just like continuously move, escape the Earth's gravity, and go off into space. So hydrogen being very light, it like Earth's gravitational pull is not enough to hold it towards itself. Like sure, some molecules end up being on Earth, but again, gas molecules are constantly moving, and if one happens to escape the Earth's gravitational force, it's gonna go off into space. Okay, that's the reason. Like all of you, I'm sure must have played at some point with helium balloons and hydrogen balloons, right? What do they do? Like, what do these balloons do if you let go of them?
They make your voice really
They fly.
happy.
The helium makes your voice, but I'm talking about the balloons. Like, if you just like leave those balloons, they just fly off into space.
They fly. But
They
is it
float.
also hydrogen? Because I only heard about helium.
Yeah, hydrogen as well. The reason why helium is more commonly used is because it's inert. Like, it's not a fire hazard. Like, you never know.
Plus, I think it's cheaper to produce, right? Is it?
Both are pretty much on par. I would say, in fact, hydrogen is easier to source because you can just electrolyze water and get hydrogen. Helium, again, you have to like identify where to get helium from, so that's more difficult. Yeah. So yeah, basically, bottom line is that you don't find it in the Earth's atmosphere a lot because it's very light, escapes the Earth's gravity, and flies off. Yeah. So that's the reason. And now let's look at the combined form. So where all can you find hydrogen in the combined form on Earth?
Water.
water.
Yes. So where all, like basically the Earth's oceans and other water sources, rivers, lakes, whatever. Where else do you find hydrogen in combined state? Water is not the only compounded forms, right?
Hydrocarbons.
Ice, but we don't have that much left.
That's water only, no? Oceans and other water.
Hydrocarbons count?
Hydrocarbons, absolutely. Petroleum products. Where else?
The methane, and that's like formed in the Bermuda Triangle.
Methane, octane, all of those are hydrocarbons only. What are you guys made of?
Any stones or something like that?
Not specifically, but yeah, hydroxides. That also like as water of crystallization only it's there. What are you guys made of, elementally speaking?
Water.
Carbon, hydrogen, and oxygen.
There you go. Apart
So
from
like a muscles or tissues.
yes, all your carbohydrates like plants, animals, all of these contain hydrogen. Carbohydrates, let's say. C6H12.
I was gonna say like plants and animals, but I thought that come under hydrocarbon.
No, hydrocarbons here we're talking about like petroleum products and stuff like that. Hydrocarbons are just carbon and hydrogen. Here, like when you say carbohydrates, proteins, you also find like oxygen, nitrogen, sulfur, phosphorus, and other things. So not just this, but also like plant and animal tissues. Basically, every single living creature is made of, like, if you count by mass, I think carbon is the highest. But in terms of if you look at the number of atoms, then yeah, hydrogen is pretty high. Hydrogen is basically a filler atom for all of organic chemistry. So valency of carbon is short by one, or there's a hydrogen atom that's filling it up. Basically treated like that. Yeah. So this is where you find hydrogen in free state and in combined state. Yeah. Okay. So going to the next part, we talk about isotopes of hydrogen. How many of you are fans of Spider-Man?
Me.
Oh, so have you guys seen the? Oh, a lot of you. Have you guys seen the
The trailer.
Tobey Maguire one?
Oh yes,
Oh,
I
yeah,
have seen
all of them.
Oh, yeah.
So one of the plot points in one of the movies is like an isotope of hydrogen there. So hydrogen, there are three isotopes. You have H11. Okay, before I discuss them, what do you guys remember about isotopes? What are isotopes? Yeah, Kavya.
Sorry, my hand was raised, but yeah, I can answer. The elements which have different atomic number but same atomic mass.
Huh? Isotopes. We're talking about isotopes. Not
No,
And,
they have the
so,
same atomic number but different atomic mass.
That is correct. So same atomic number, different masses. Okay. So hydrogen has three isotopes. You have H11, the one you guys are familiar with, and then you have H12, and then you have H13. Okay, so this is the most common. This is like the dominant isotope of hydrogen. So this particular thing is called protium. So if at all randomly you come across the word protium when you're reading any science article, magazine, something like that, don't be confused. It's just your normal regular hydrogen, this particular isotope of hydrogen. H, if the mass number is 2, this is called deuterium. And this particular hydrogen isotope is called tritium. Okay. So, I mean, the Spider-Man, Tobey Maguire Spider-Man, I think part 2 mein, the bad guy basically tries to harness tritium and, wants to create his own sun on Earth. Some plot point related to that. Yeah. I don't know if you guys remember it or thought that in that movie.
Doctor Octopus.
Yeah. Octopus. Okay.
He's in the new movie also. It'll like launch after a month.
Oh, it's gonna be bad.
Yeah.
I don't
Yeah,
know.
like all of the villains from the
Yeah,
past
like
Spider-Man
sequel.
movies are like gonna come in this movie. It's like the end of the trilogy of Tom Holland Spider-Man movies.
Oh yeah, all those home movies, right? far from
Yeah. So like the
homecoming.
first one was homecoming, then the second one was far from home, and this one's gonna be nowhere home.
Cool. All right. So these are like the three names for the three isotopes of hydrogen. Protium doesn't have any special symbol. I think this is regular H. Deuterium, sometimes instead of H, if you find D in chemical compounds, this is what it stands for. It's basically hydrogen, it's the isotope of hydrogen. And tritium is given the symbol T. If you find any like T2O or something like that, then it's basically water molecule, except you have H3 instead of H1. That's it. Special points about, so before we get to the special points about them, how many neutrons does protium have?
One.
Is it?
Wait, sorry, I thought you were asking the second one. The first one has 0.
Yeah. Mass number is 1, and that mass is coming from its single proton. That makes it hydrogen. So 0 neutrons. Deuterium has how many neutrons?
1.
1,
And tritium has how many neutrons?
2.
2.
Is there a difference in the number of protons that they have?
No.
No, electrons and protons are same. It's just that the neutrons are.
Yes. So electrons, protons are the same. Only difference is in the number of neutrons. Some special notes. Oh yeah, tritium is the radio.
Ma'am,
Yeah.
I got disconnected. I was there till tritium. After that, I kind of got disconnected. Could you repeat?
Same thing, whatever you see on the board, Rishad. So these are the symbols given to them. Deuterium represented by D and tritium represented by T. And these are the number of neutrons that they
Okay.
have. So special notes, like tritium is the radioactive one. Deuterium, you find, like protium is the most predominant one, like 99.999% of it is basically protium only. You find. Deuterium, you find it to some extent. There's some percentage given in the textbook. I think it's like 0.0156% or something like that. You usually find it in the form of H2, not the television. Instead of H2 molecule, like one atom is protium and one atom is deuterium, something like that. H2.
What does the D stand for?
Huh?
What is HD?
H is protium, D is deuterium. Like molecule dihydrogen is H2, right? So when both the atoms are H and H, you write it as H2. Deuterium, sometimes, like if at all you find it on Earth, it is of the form like one atom is deuterium and one atom is hydrogen.
So it's still H2 only.
H2 only. You use D to indicate that one of them is this isotope.
Which one is radioactive?
Tritium is radioactive. It like I put it as a table only. So deuterium.
Protium is just protium.
Protium is like your regular old hydrogen, same thing. Oh, I meant to write predominant. Good catch. So protium is the most predominant hydrogen that exists. Matlab, this is what is available like all the time. 99.9% is this hydrogen. So this is more like 0.0156% or something like that. Like just check this particular percentage. Exact number I don't remember right now. Tritium is like even more rare. It's like 10 to the power minus 3 or something like that. For every atom of regular hydrogen, or basically like tritium is 1 in 1,000 or something like that. It's very, very rare. The least quantity. Least how do you call it? Least amount. Very rare. Yeah.
Ma'am, so can deuterium and tritium be formed in laboratories?
Yeah. So whatever reactions are happening in the sun, right? Like deuterium and tritium are formed by the fusion of hydrogen. So if you can you know, if you have laboratories like CERN does, where you can perform fusion experiments and all that, you can produce deuterium and tritium.
Won't it be very dangerous though?
Yes, it would be. That's why you need to invest a lot, and that's why it's just like one or two places on. That's it. So the source for deuterium is so there's something called exhaustive electrolysis. The principle behind it, you can understand it this way. So deuterium, we know that it's there, just that it's very, very rare. So you keep eliminating all the hydrogen that's present until you're left with a lot of deuterium atoms. That's kind of how to isolate it. So you guys done noting this down? Can I change the page?
Yes, ma'am.
Cool. So let's if you compare hydrogen, deuterium, and tritium, what can you say about their chemical properties? Would it be the same or would it be different?
Could you repeat once?
If you compare protium, deuterium, tritium, the three isotopes of hydrogen, what can you say about their chemical properties? Will it be same or will they differ in the chemical properties?
If the number of electrons are the same, then there shouldn't be much difference in the chemical properties.
Absolutely.
Tritium would be different.
Why?
It's radioactive, right?
It's radioactive, but its chemical reactions, what sort of compounds will it form with oxygen or halogens? It's all going to be the same. Like valency will always be 1. It will still form covalent bonds.
Yeah, that makes sense.
Yeah. So that way, chemical properties are pretty much the same because same electronic configuration. That's where your chemical properties come from. Number of available orbitals and number of electrons available for bonding. Yeah.
Radioactivity would depend on the nucleus, right?
Yes.
Why the number of
yes, protons and neutrons. The only difference, if you were to compare in the chemical properties, will be it's more of a nitpicky sort of a difference. It'll be in the rate of reactions. So the only difference is in the rate of reactions. So rate of reaction, the end product will be the same. Like protium will form H2O, deuterium will form D2O, but how quickly are they going to form? That's where the difference is going to be. Yeah. So basically, the way they react will be the same. It's just how quickly or how slowly the rate of reaction is what is going to be different. So this difference, why is there a difference in the rate of reaction, is because of the bond dissociation energy. So in your textbook, there's a table that compares all the properties. Let me just pull it up.
So which one would have the more rate of reaction? Like which one will react faster?
Wait, let's look at the values and then we can figure it out. Comparison of number of protons, neutrons versus the melting point, boiling point. There you go. Okay, so you can see property here, we're comparing protium, deuterium, and tritium. Atomic mass, we know there's a difference. Electrons, protons, neutrons, we discussed. Nuclear stability, stable, this is the radioactive one. Molecular form में H2, D2, T2, they all form like a diatomic molecule. Abundance, there you go. Yeah, not so far up. 99.9% is protium, 0.015% is deuterium. Tritium is even way lesser than I expected. So the ratio of protium to tritium is almost 1:10 power 16, like 10 power minus 16. So every 10 power 16 atoms of protium, you find one atom of tritium. It's kind of like that. This is like way too rare. Molecular mass of the, like we're talking about molecular mass, double the atomic mass. And then you have comparisons of melting point, boiling point. Internuclear distance. So basically, if you compare protium, deuterium, tritium molecules, like chemical bonding may you guys learned, right? So they come at a specific distance where the bond can be formed. So if you compare the distance between all three, it's pretty much the same, 74.14. It is exactly the same, much meters. Critical temperature, well, if melting boiling points are different, critical temperature is also slightly different. Enthalpy of dissociation. This is something that you guys have not studied yet, but do you guys have any idea, like what do you think this means? What is enthalpy of dissociation?
Not sure, but
it takes to break a bond.
Energy required to break the bond.
Kaveri, was that the same thing you had, or were you going to say something different?
yeah, the same thing.
Yeah, that's exactly it. Enthalpy is like the measure of energy. How much energy is it taking to dissociate, matlab break this particular bond? So atomic hydrogen is taking 435.9 kilojoules per mole. Deuterium is taking 443, and tritium is taking 446. So you can see there's slight different, but still there's a difference, right? So it's taking more amount of energy to break the DD single bond and the TT single bond, which is where your difference in the rate of reaction is coming from. So if it takes more energy to break the DD wala bond than the HH wala bond. So HH bond breaks more easily. This will go ahead, continue the reaction. DD is going to be slower because it's taking a lot more energy to break this bond. Okay, so that's where the difference in the rate of reaction is coming. Okay. Okay. So chemical properties, you can see, internuclear distance, ionization, enthalpy, like all of that, like valency, electronic configuration, all of that is the same. So chemical properties will be the same. But because of this one factor, the rate of reaction is going to differ. Right? So you can take a note. So difference is in the rate of reaction due to the difference in bond dissociation index. Yeah. So make a note of this, then we'll discuss physical properties. So physical properties, we're going to, like, physical properties entail your boiling point, melting point, density, critical temperature, like all of this sort of stuff. So boiling point, melting points are related. You have your enthalpies of fusion and vaporization. Yeah. So what can you say about the physical properties? Will they be the same or will they be different?
They would be different.
They will all be different. And why, where is the difference coming from?
Because of their masses.
Absolutely, yes. So more mass means more boiling point. So such a stark difference in masses means all of these are going to be different. Yeah. Cool. Let me know when you guys are done noting this, then we'll go to the next part.
We don't have to know the details of it, like density and enthalpy.
No, like because of the difference in masses, in sub में difference आएगा ही. Like the kind of questions I'm anticipating is know which properties are going to be the same, which properties are going to be different. So MCQs may you may be given 4 options like reaction with oxygen, then melting point, then enthalpy of fusion and density. Pick in which case will the property of hydrogen, protium, deuterium, tritium are going to be different. Things like that. Or maybe you may get an assertion reason type of question. They are going to have similar melting points because of so and so. Then you need to know that they are not going to have similar melting points. Okay, that way. So इसके बाद है textbook में we have physical and chemical properties of hydrogen, which is deleted, but it's not very difficult. It's like hydrogen ka reaction with halogens, with oxygen, like group 16 elements. What sort of bonds does it form? Ionic, covalent, all of that. That and all, like you're going to study when you study those other elements anyway. So that's possibly why it's deleted. But abhi ke liye, the striking thing about hydrogen ke compounds are hydrides. So hydrides are basically like you can think of them as a shorthand for hydrogen compounds. So hydrogen basically is able to form a compound with almost all elements except noble gases. Noble gases, the privilege is only for oxygen and fluorine. No other element can form a compound with them. So except noble gases reacts with every element, and depending on which element it is, it forms like a different type of hydride. You guys have already are familiar with some of the hydrides, like HCl is a halogen plus hydrogen compound. That's a type of hydride. And then you have ionic hydrides that it forms with like sodium and all of that. So that way, there are 3 types of hydrides. Basically, hydrogen compounds are classified into 3 categories. You have ionic hydrides, also called saline hydrides, saline, saline, whatever you want to pronounce it. Then you have covalent or molecular hydrides. These exist as separate molecules, like HCl is a molecule, H2O is a molecule, and all of these are covalent compounds. So covalent or molecular hydrides. And this is something new for you guys. This I'll spend some time on. The third category is interstitial hydrides. Interstitial, also called non-stoichiometric. So ionic covalent is pretty easy. These are compounds that you are familiar with. You get a hang of it easily. Interstitial is something that we'll spend some time discussing. Okay.
Ma'am, interstitial one is also known as
Non-stoichiometric. Remember stoichiometric?
Oh yeah. Okay.
Non-stoichiometric. Discuss करते हैं like हर एक का. Why this particular name? What is the meaning behind it? The name hydrides is pretty easy. Like oxygen से compounds जो form होते हैं, you call them oxides, right? So basically, ide is basically the suffix used for like अगर उसका oxidation state is less, like if it's like less than the other thing, then you use a suffix ide, like oxide, sulfide, nitride. That way hydrogen से जो compounds form होते हैं, call them hydrides. Okay, so can I flip the page?
Yes, ma'am.
Did.
Yes, ma'am.
Yes, ma'am.
So the first thing we talk about is ionic hydride. If anyone's yet to note, let me know. I'll put it back. Otherwise, we'll continue. Ionic hydride. Also called saline hydrides, like I've mentioned the name there. Just check video for it. Okay, so ionic hydrides, like the compounds that fall under this category. So when H2 gas forms a compound with any element from the S block. So it forms these hydrides of the form, let's call it EHX. So value of X will depend on the valency of this element. So when the element belongs to S block, you get S block metals, you get ionic hydrides. Here, so we'll look at some properties of ionic hydrides. So the first thing is they are stoichiometric hydrides. So stoichiometric in the sense, the ratio of the like number of atoms of the element to the number of atoms of hydrogen, it's all small whole numbers. Like for example, अगर सोडियम के साथ फॉर्म कर रहा है तो फॉर्मूला क्या होगा? Any of you can predict?
NaH.
NaH.
1:1. Correct. Magnesium के साथ फॉर्म कर रहा है तो what will it be?
MgH2.
MgH2.
Yes, there you go. Then similarly, you have BeH2. So these are all stoichiometric, like the ratio NaH में it's 1:1. MgH2 में it's 1:2. BeH2 में it's 1:2. These may seem obvious right now, but This is not the case with interstitial hydrides. That's why we call them non-stoichiometric hydrides. Why is that difference coming in? Like we'll discuss when we do that. But for now, remember, like stoichiometric matlab, the ratios of, how many atoms of one element to the other, like inka compositional ratio is all like small whole numbers. It's according to the valency. It's all proper, perfect. Yeah. So these are ionic hydrides. These are some examples. LiH is another one. LiH is pretty important because that's the hydride that's used a lot of places. Okay. So out of these, specifically BeH2 and MgH2 are polymeric. Polymeric matlab all the MgH2 molecules or BeH2 molecules are associated with each other. Like they are all bonded to each other in some way. They basically form a polymer. And along with this, BeH2, LiH and MgH2, these three are significantly covalent. Like they show a lot of covalent bond K properties. Do you guys remember Fahan's rules when we were doing chemical bonding?
Yes, ma'am.
So even though S block elements form ionic compounds, like yes, sodium, potassium, calcium, like all these other compounds are purely like they're ionic, but the smaller molecules, like because of their small size, high polarity, they show significantly, like they show a lot of properties of covalent bonds. Like that's where your polymerization is also coming from. They're all just associated with each other. Okay. So these three, like remember, they are kind of special within the ionic hydrides that they show a lot more covalent nature than the rest. And BeH2, MgH2, they polymerize. They polymerize. Okay. So
I
apart
didn't
from,
get it. Why was it significantly covalent?
they're not purely covalent. They show a lot of covalent bond K tendencies or properties.
What do you mean when you say like they polymerize? I didn't get it.
Polymerize matlab, like let's say you have BeH2. Then this is going to form like a bond with another BeH2. Because beryllium is kind of electron deficient, right? When you look at it from Lewis's thing. So this way, multiple BeH2 kind of bond with each other, end up being like, this is like polymerization, polymer. So it's like multiple units coming together. So when they associate with each other like this is called polymerization. When only two units join together, like that happens with some oxides of nitrogen, it's called dimerization. When you have like really long chains, multiple molecules coming together, it's called polymerization. This is kind of how it exists. When BeCl2 shows some polymerization. Yeah. Boron Carbohydrates, that dimers. That's why instead of BH3, you write it as B2H6. That we'll study when we do like group 13 carbohydrates. So so this is polymerization, when multiple units come together to form like a large chain. That's polymerization. Like your plastics are also formed this way. Like you have organic compounds, small units joining together to form like a large single chain. That's polymerization. Okay. Then general properties of ionic halides. Since most of them, again, they're ionic, right? So they are crystalline, like just like salts, you find them as crystals, solid state at room temperature. They are non-volatile.
Ma'am, sorry to interrupt, but I still didn't get it about the polymeric. What was it exactly?
Just like instead of existing as independent BeH2 units, it basically bonds with other BeH2 units to form like a long chain. That's polymerization.
Like plastic, right?
Yeah, like plastic. That's why plastics are called polymers. Yeah, coming to properties, they're crystalline, non-volatile. They're when we talk about conduction, they're non-conducting in solid state, just like ionic compounds. But they do conduct electricity in molten state. Makes sense. I mean, if you have like suppose you have Na plus and H minus, molten state में ions are free flowing, so they can conduct electricity.
This is ionic hydrogen.
Yeah, all these are properties of ionic hydrides.
So basically it has all the properties of ionic bonds, right?
Yeah. Yeah, that's exactly why they're called ionic hydrides. And the other name, saline hydrides, because again, saline solution salt is like NaCl, right? So something related to that, some connection there, I guess. Yeah. So one more point talking about the properties. So we say that they can conduct electricity in molten state, right? So if I take molten,
Could you go back, please?
yeah, finished writing. Yeah, let me know when you're done, then we'll discuss that. the polymeric form of BH2, I made a tiny little mistake. So BH2 ka shape will be linear. So opposite sides, these two will be like solid bonds. These two will be like solid bonds. So, which one I put as dotted? Mistake there. But yeah, essentially this is kind of what it's going to look like. The polymeric diamond. This B will be bonded to this and this. This B will be bonded to like let's say this and this. यहाँ पे this where hydrogen is there, we have some association. Okay. Should you guys done? Should we discuss the next part?
Yes, ma'am. I
Yes.
completed.
Yes, ma'am. Done.
Okay. So ionic hydrides, they can conduct electricity in the molten state. So if I take NaH, melt it, so it's in the liquid state, and apply electricity. Okay. So this is going to like NaH is going to dissociate into different ions, right? So experimentally, what was found out is that there was H2 liberated at the anode. So on passing electricity through molten hydrides, molten ionic hydrides, H2 gas was liberated at anode. What does this prove? What can you say based on this? Do you guys remember what is cathode, what is anode?
Yes.
Anode was the positive terminal, right? Because it attracts anions.
Correct. Anode is the positive terminal and it attracts anions. That is absolutely correct. And if H2 gas is liberated at anode, what does it mean? Like what is there in the solution?
Positive charge.
Anode is positive charge, yes. Like we have connected it such that one electrode is positive, one electrode is negative. तो ये सेटअप हमारे कंट्रोल में है, हमने किया, let's say this is the cathode and this is the anode.
Hydrogen would be negative, like electronegative.
Anode is positively charged, cathode is negatively charged. Now the result is that it is observed like यहाँ पे एक molten hydride डाल के we passed electricity through it. So we saw that this side we were getting H2 gas. So agar H2 like hydrogen are clumping together around the anode, which is positively charged. So basically this experiment or this phenomenon proves the existence of H minus ions. So we're getting hydrogen gas because the negatively charged ions which this anode is attracting was hydrogen ions. So what was happening at the anode was that 2H minus molten state, liquid state, were coming to the anode, forming hydrogen gas and giving up like 2 of the electrons here. So this was the reaction at anode. Yeah. So this particular phenomenon or this particular process happening, that if you take a melted ionic hydride and you pass electricity through it, you're getting H2 gas at anode. This proves that अच्छा अगर हाइड्रोजन एनोड के पास आ रहा है, it means hydrogen exists as negatively charged ions. इसीलिए it's getting attracted to the positively charged anode and undergoing this particular reaction to give hydrogen. Basically, it like proves the existence of H minus ions. Or instead of saying proves the existence of, let's say confirms the presence of H minus ions.
So basically, in the molten state, when we do electrolysis, what was it called? The process?
Electrolysis.
Electrolysis. Then when H2, no, sorry. Yeah, H2 would go to the anode, only then it would be proven. It's only that, right?
Yeah, like because we are getting
the existence of hydrogen.
Yeah. See, pehle, like you guys have seen these kind of cases. Like if I take NaCl, molten liquid state, and if I pass electricity through it, cathode के पास क्या मिलेगा हमें, anode के पास क्या मिलेगा in this scenario? So this also breaks down into Na plus Cl2, right? Now यहाँ पे क्योंकि Cl is the negative ions, you're going to get chlorine gas at the anode. तो हमेशा जो भी negative ions है, that you're going to get at anode. Whatever is the positive ions, you're going to get at the cathode. So when we took ionic hydrides, did the same thing, like melted it, passed electricity through it. People observed that you're getting hydrogen gas at the anode. And the only way you can get hydrogen gas at anode, because this is not aqueous solution, right? Like you only have positive, like 2 elements in it, jo bhi, like sodium, potassium, whatever you're taking, and then you have H minus, ionic hydride. So anode के पास H2 आ रहा है, मतलब in that particular situation, in that particular compound, hydrogen is existing as H minus. So basically this confirms the presence of H minus ions. ठीक है? Cool. We're done with this. Go to the next part. Oh, there's more properties. Okay. Another property is, again, this is like a basic reaction. They are soluble in water, but when you put them in water, they react very violently. So they react violently with water. So when you put any hydride, like let's take sodium hydride only, dissolve it in H2O. This is solid. You end up getting NaOH, the aqueous solution, because you're conducting this in water and hydrogen gas is released. Okay, so these hydrides, like sure, they may be non-volatile in solid state and they may be crystals, but they tend to be extremely reactive. At least the ones with the higher metals like sodium, potassium, rubidium.
If they are soluble in water, then how are they reactive with water?
Soluble matlab it's dissolving and it's doing more than dissolving. It's breaking down into its constituent ions and it's reacting because it's more stable this way.
Hydride, right?
Huh?
Hydrogen or hydride?
Hydride. The hydride, like this particular substance is, when you mix it in water, it reacts violently to give hydroxides. You can put this here, react violently with water to produce hydroxides.
Ma'am, for the above experiment, like the cathode and anode one, there also we needed water, right, for the reaction?
This is molten. You're passing it through molten ionic hydrides. If you mix it in water, it's going to end up becoming this. So, no question of using aqueous solution. It's a violent reaction. So, like spontaneously, it's going to just like releases a lot of energy also. It's going to get hot. Noted?
1 second.
Huh.
Done, ma'am.
Cool. Is everyone done? I mean, close? Okay.
Yes.
Cool. So normally ionic hydrides are pretty reactive, but lithium hydride specifically, it's not as reactive as the others with oxygen or chlorine. So let's say it is unreactive at moderate temperatures. Let's think of it as room temperatures, normal, like middle temperatures, with oxygen and chlorine. Now this part, it's important because, because ionic hydrides are extremely reactive and they're producing hydrogen gas, right? So a lot of these are like, it's convenient to use them as reducing agents. Like whichever reaction you want pure hydrogen in, like gaseous hydrogen is difficult to store and transport, right? But if you were to convert them into solid crystals, you can handle them much more easily. So convert them into LiH. Other hydrides, they are reactive. So again, storage, transportation will become a little difficult. But because this is unreactive with oxygen and chlorine in general, what like advantage of lithium hydride is it is ideal for producing other useful hydrides. The most common useful hydride that is known in chemistry that you guys are going to come across a lot more is lithium aluminium hydride, and sodium borohydride is one, lithium borohydride is another. So you take lithium hydride, make it react with aluminium chloride. So this is the dimer form of AlCl3. You can observe that here. This gives lithium aluminium hydride, LiNH4. This is a very good source of hydrogen. So if you want to produce alcohols or aldehydes, you just take a carboxylic acid or an ester, make it react with lithium aluminium hydride, and that's a very convenient reaction for reduction. Similarly, lithium borohydride as well. Just for your information, yeah, this compound is called lithium aluminium hydride. This compound B2H6 is called diborane. This also is used as a reducing agent. This compound is called lithium borohydride. Similarly, you have sodium borohydride. I don't know if you would have come across LiLH4 in like right now in hydrocarbons, but I know like बाद में like alcohols and carboxylic acids. That context, yeah, this keeps coming up every couple of reactions.
What are the uses of LiAlH4?
So all of these are good reducing agents. Like source of hydrogen, right? And addition of hydrogen is reduction. They used as very good reducing.
Are all hydrides good reducing agents?
They are, but again, because they are violently reactive, it becomes difficult to handle them. Lithium specifically, compared to the other hydrides, it's little unreactive. Like you can control it. You can make it react when you need it to react. So that's why this is more widely used.
Ma'am, I have a small doubt. So if they're unreactive at moderate temperature, then how are they like in Al2Cl6? So they won't react if it is only Cl or O2, or they can react if it is in a compound like O2 or Cl2. If O2 or Cl2 is in a compound, then they can react. Or
yeah, like if there's oxygen, moderate temperature with oxygen, so you can be assured that it's not going to decompose off if you leave it outside for some time in there. And secondly, if they're unreactive at moderate temperature, you can control the reaction. You can increase the temperature slightly, or you can increase the temperature a lot more to get your desired product. So the control is in your hands. But if it is reactive at like all temperatures and all, it'll be difficult to control that reaction. That's why it being unreactive and especially not reacting with O2Cl2 is ideal. But at the same time, if it is unreactive at all temperatures, then it's going to be a task to get it form this compound in the first place.
so it won't react like Al2Cl6. So that compound, it won't react with it if it is in a moderate temperature, or it will react since aluminium is there.
Moderate temperature, it won't. Like if you put it in the fridge, if you keep it in cool conditions, it will not react. You slightly increase the temperature, you control the conditions, then it's going to react. So let me know when you're done with this, then we shall get on to covalent or molecular hydrides. hydrides. Yeah, added this one. Abid and Ritu are done. Okay. Smita is done. Sanat, Rishit, Kaveri. Kaveri is also done. Sanat, Rishit, and Arnav. So let me know when you guys are done. Okay, Arnav is also
None, ma'am.
done. So next one, we'll talk about covalent or molecular hydrides. Yeah. So ionic was with group S block elements, group 1 and 2. So covalent, what do you expect? So hydrogen reacting with elements gives again EHX, or formula can be like EMHN also, like other things. So what do you think element E could be to form a covalent hydride?
Carbon,
Only carbon?
silicon.
Carbon, silicon, partly right. So E is basically a P block element. Yeah. So S block के साथ ionic hydrides आए. P block elements के साथ you get covalent or molecular hydrides. So examples, I've mentioned a couple of them earlier. You've got HCl, HF, group 17K. You've got H2O. This is also hydride, taking the format of EMHN. So this is also like EHX or OH2. Then you have NH3. With carbon, you have CH4. So all of these are P block elements. You have some examples. So silicon, yes, SiH4 also. So in this, hydrogen is not existing as H minus, but it is considered as a hydride for convenience. Basically, we just classified all the hydrogen के साथ compound बना रहा है, मतलब as a hydride. Considered as hydride for convenience, basically. And because they are covalent compounds, they exist as individual molecules. It means that they are volatile. Volatile matlab they can turn into gaseous state easily. Low boiling points. Now within covalent or molecular hydrides, we again classify them into 3 types depending on what type of a molecule it's forming. You can just like divide your book into 3 parts, form a table. It's easy to study it as a comparison. So this one is classified as, the first one is electron deficient, covalent hydrides. Then electron precise. And you have electron rich. So note this down, then we'll discuss each point one by one.
I understand that line hydride for convenience, covalent. So all time.
So hydride, I mentioned, right? Like oxygen compounds called oxide because valency is O2 minus. Usually you use the suffix "ide" for when it's forming a compound with that element alone and it's existing as anion. But p-block elements ke saath, it's a covalent compound, right? Like hydrogen is not even taking the role of the anion here, even when you split it. Like HCl splits as H plus Cl minus. But still, these compounds are classified, we call them hydride for the sake of convenience. So basically, whichever element it is, it's forming a compound with hydrogen, so usko hydride bulate hain. That's what happened basically. Usually hydride, if you hear the name hydride, usually people think acha H minus jisme hai usko hydride bulate hain. But in this particular case, hydrogen is not taking a negative charge. So technically they are not hydrides, but we classify, we put them under hydrides for the sake of convenience.
Okay, got it.
So, okay, can we start discussing this? You guys done?
Yes.
Okay. So electron deficient hydrides, you put those compounds in this category where like these compounds basically have too few electrons for writing the conventional Lewis structure. So I'll just write the point here and then I'll discuss it. Okay. Do you guys remember Lewis's rules? What did Lewis say when he was discussing like covalent compounds and structures? Okay.
Can you repeat?
So do you guys remember what was the rule that Lewis was talking about when he was, talking about drawing the structure of molecules and all? What rule did Lewis give?
That like you'd use the symbol of the element to represent it. There would be dots and crosses as the electrons and a line to represent the bond.
Yes. Like how do you figure out ki kitne bonds rahenge around a particular element? What was the rule he was talking about?
I
Octet.
didn't get it. Like
Smera got it. So Lewis's octet rule. You guys remember that?
I forgot it was his rule.
He was the first one to talk about it essentially. Lewis causes postulates. Yeah. So octet rule. So like if you were to draw the Lewis structure, you usually follow the octet rule, right? Like 8 electrons around each atom. And hydrogen ke case mein 2 electrons, but yeah, the noble gas configuration complete hona chahiye. But some compounds, like basically electron deficient hydrides mein kya ho raha hai na? The central element there are too few electrons, like the octet is not being satisfied. So noted example in this case is again diborane B2H6. So essentially boron के compounds मतलब you can think of them as BH3. So you have boron, 3 electrons है उसके पास. Hydrogen shares 1 each. And boron doesn't have like 8 electrons. It only has 6 electrons in the outermost shell. That's kind of why it exists as B2H6, forms a dimer because it is electron deficient. But yeah, so those kind of compounds where the octet is not being completed, they come under electron deficient hydrides. Yeah, so B2H6 is an example. And yeah, iska name, you can write it again here. This is called diborane. Borane, diborane, because it's like 2 of borane. Borane, because it's like similar to methane, except it's with boron. So you can remember this easily as diborane. And in the same way, just like boron, it is formed by group 13 elements. So can you guess based on the same point, अगर electron deficient में octet complete नहीं हो रहा है, if there are too few electrons, electron precise में what will be the case?
Exactly satisfying the octet rule.
Absolutely. So there's required number of electrons for writing the Lewis structure.
Ma'am,
Ma'am?
even if one shell is like octet satisfied, then where it will come, electron deficient or electron precise?
One shell, like all of these cases, if we are talking about shell octet satisfying, it's going to be the valence shell only. So if it is not being satisfied less than 8 electrons hai, to deficient hoga. If there's exactly 8 electrons, all of them being shared, to electron precise hoga. Example is CH4. Carbon has 4 electrons. Hydrogen के साथ share कर रहा है. It's all complete. And electron rich is basically if there's excess electrons present as lone pairs. Ritu and Kaveri, yeah, what's up?
I just reconnected. I understood like the electron like precise, but I didn't understand like what the last line of electron deficient was. Like, what does it mean when you say formed by?
Ritu, your voice is breaking. Can you just repeat your question?
I think she asked about electron deficient. She missed that part.
Oh, so electron deficient.
Could you explain like the last line?
Formed by group 13 elements. This.
Okay, understood.
G13 is. Yeah, Kaveri.
I lost my connection when you were explaining electron deficient. Could you just go over that briefly once more, please?
So electron deficient is if you have like normally Lewis structure लिखने के लिए you follow octet rule. There needs to be, if there's a covalent bond being formed, 8 electrons होना चाहिए. But there are some compounds like B2H6 or BH3. Like boron has 3 electrons. Hydrogen shares like 3 electrons with it. And this is the structure of boron hydride. And there's only 6 electrons around boron. It is less than the required 8 electrons. So if there's too few electrons for writing the conventional Lewis structure, you call that as Lewis electron deficient state. So electron.
But we can still use that structure, just that it's deficient, but we can still represent it.
Yeah, this is the Lewis representation only. Just that, Lewis first talked about octet rule, wo follow nahi ho raha hai. Less than required number of electrons. That's why this is electron deficient. Electron precise, whatever electrons are there, there are 8 electrons and all of them are exactly sufficient to form that hydride. Electron rich, if at all you have any electron present as lone pairs. So example is water and HCl, any halogen ke compound, you have lone pairs present on all of these. Water has 2 lone pairs, halogens have 3 lone pairs. So, yeah. Okay. Similarly, how you have electron deficient formed by group 13. Group 14 forms electron precise.
Is there like a reason why group 13, group 14 form so?
Yeah, I mean, you can see it logically. Group 13 has 3 electrons in the outermost shell. So 8 electrons complete nahi hoga na if 3 of them are shared with hydrogen. And group 14 have exact 4 electrons in the outermost shell. Hydrogen shares 1 more. So 4 into 2, 8 ho gaya. It's like precise, the exact number required. And groups.
Why 4 into 2?
Because hydrogen is sharing 1 more electron, right? So 4 electrons of that element plus 4 more from the 4 hydrogens.
I didn't get it. 4 more from 4 hydrogen.
Like let's take carbon. Carbon has 4 electrons.
Yeah.
Yeah, so hydrogen is sharing 4 more. So everything will get double.
So if it is formed by like electron precise, the number of hydrogens has to always be 4.
Yeah.
And similarly, if it is electron deficient, it always has to be 6.
It turns out to be 6. Yeah, there's less than 8. Group 13 is the only one that can form that. Agar group 15 hai, so there's more than required number of electrons. So there are going to be some electrons left over as lone pairs. Even ammonia, nitrogen has 1 electron pair extra. It's just classification key. Oh, these are the types of compounds we found. So let's split them up. Let's classify them so that it gets easier for study. So these are like the basic definition. Special notes, electron deficient usually form something called Lewis acids. Are you guys familiar with or aware of Lewis acids, Bronsted base, and Lewis base?
I've heard of them before, but I'm not sure what they are.
Okay, you just
No,
heard
ma'am.
the words. Sanat?
I haven't even heard of them.
Okay. You will get familiar with them this year. There's a chapter called Equilibrium that's all about acids, bases, and salts. Yeah. So usme you have definition of Lewis acids, Lewis bases, Bronsted acids, Bronsted bases. And we have Arrhenius acids, Arrhenius ka definition of acids and bases. So Lewis acids are basically like species that can accept electrons, electrophiles in organic chemistry. They act as Lewis acids. And you can see why. Like if you have electron deficient compounds like B2H6, this is not a hydride, but AlCl3 is also a Lewis acid. FeCl3 is also a Lewis acid. Basically, wherever you have electron deficient compounds, they're deficient in electrons, so they're capable of accepting more electron pairs from those that are rich in it. So they are called Lewis acids. Electron acceptors, basically. You can just remember it as electron acceptors, not Lewis acids. The
Ma'am, so
behind it, we'll discuss in detail when we talk about acid species. Yeah, Rishit?
ma'am, a small doubt. So, like when the electron deficient ones, as it is written, they accept electrons. So, the valence shell would have like 2, 3, or like or like 6, 7, or something like that. 6, 7 would be called electron rich or electron deficient in the valence shell.
Like after the compound is formed, usually they have like 4 or 6 electrons, something like that. It also depends on the orbitals. Like if you get into FeCl3, there again, like there's empty d orbitals present that can accept electrons. So you have to look at the electronic configuration. I can't like generalize it and say it. Maximum generalization we can do is if they're electron deficient. Like if they have more empty orbitals that can accept electrons, then yeah, they'll accept electrons and they're called Lewis acids.
Ma'am,
Yeah.
if the electron deficient ones accept electrons, then would the electron rich ones donate them?
Absolutely. So we're coming one by one, right? We're talking about the special points of each. So electron deficient ones are called Lewis acids because they accept electrons. Electron rich ones, as Kaveri said, since they have lone pairs that can be donated, they form Lewis bases. Like by Lewis definition, that's why ammonia is classified as a base. So the lone pairs that are there, the lone pairs are donated to other ligands. Like that's where the basic property comes from. And electron precise are neither acidic nor basic. Like methane is not an acid or a base. The special thing that you can just tell about them is they have tetrahedral shape. That's it. We'll talk more about electron deficient and electron rich ones. So these are Lewis acids. They are Lewis bases. Another speciality about electron rich ones is that they're formed by group 15, 16, 17, right? And what do you know about the electronegativity of these group elements?
High.
They're extremely electronegative.
They're extremely electronegative. So these hydrides, like ammonia, water, HCl, HF, they tend to form hydrogen bonding. Like they have very good hydrogen bonding, which leads to the association of molecules. They all clump together, basically. So just I'll put this in the next page, okay? Because there's hardly any space here. So if you've noted rest of the things, I'll flip the thing.
Ma'am,
Yeah.
can we take a little break now?
Yeah, all right. It's 4:36, right? So we'll finish this. So next one is interstitial anyway. So we'll resume at 4:45. You can note this, hydrogen bonding leads to association of molecules. Like they all clump together basically because of hydrogen bonding. Yeah, that's the final thing. This is all about
leads to
association of molecules. All right, I'm writing hydrogen bonding here, but if you have subjective papers and all, like don't write H bonding, write the whole word hydrogen bonding, okay, when you present it in the exam.
So these statements like electron deficient, precise, and rich are once they combine with the element or before it.
Classification of hydrides. We're talking about the hydrides here, not the elements. These are the compounds with hydrogen, जो है, like all these HCl, HF, H2O, and H3, B2H6. We are classifying these hydrides into deficient, precise, or rich.
And
Ma'am,
then
can you
the
just go back to the
ones
previous slide once? I think I forgot to note one thing.
Okay. Yeah, Rishan?
and the ones which are called like deficient, as I asked before, so I still could not understand. So the ones that are deficient are the ones having the lowest electron in the valence shell, or the ones having more but of need of like 2 or 4 electrons to complete the octet?
The second one, like they need some more electrons to complete the octet. Like compound form करने के बाद भी उनका octet complete नहीं हुआ. That's why they're deficient.
And the rich would be like the valence shell would have only like 2 electrons or 4 electrons that
No,
they can give away.
which is yeah, a lone pairs होना चाहिए. Like water is H2O. Like ठीक है, hydrogen के साथ bond किया, octet is all fulfilled, everything is fine. After that, also oxygen has 2 lone pair of electrons, so that's why it's electron rich.
Done, ma'am.
All right, guys, let's resume at 4:45. Not much. We just discussed interstitial hydrides. Uske baad water is there, heavy water is there. That's it. And hydrogen is there. Interstitial is the major one. Like water, you guys know of water ke properties, reactions, and all anyway. That should be done. Right, you guys back? Let me know when you guys are back, okay? Like put some sort of indication here. Cool. Who's having pizza?
I don't know why that was like there in my most used, and I just clicked on it.
That seems like on theme. Smira is here. Anat is here. Right. Kaveri and Rishit, you guys here?
Yes, ma'am.
Cool. Rishit, you back? Hello. All right, I'll start anyway. Okay, so ionic, so what elements did we get with ionic hydrides? Like what elements had to react or form compound with hydrogen to get ionic hydrides?
Yes, bro.
Like elements.
And what about molecular ones, molecular hydrides?
P block.
P block. So the remaining category, interstitial hydrides, what elements do you think would react to form interstitial hydrides?
D block or F block.
Block.
There you go. Both D block and F block. So they're formed by many D block and F block elements, not all of them. Like which ones don't form hydrides, we'll look at them. So essentially D block, F block form interstitial hydrides. So the ones that don't form interstitial hydrides are, so they're not formed by groups 7, 8, 9. So the elements present in groups 7, 8, 9, basically you don't find hydrides being formed with manganese, iron, cobalt, ruthenium, you have rhenium, osmium. You can look at the periodic table, basically the ones under 7, 8, 9. The most common one that you guys would be familiar with are manganese, iron, cobalt. Like इसके नीचे जो भी है, they don't form hydrides. Okay. And within group 6 also, only chromium is the only one that forms the hydrides. Cr alone forms. Like rest of the elements of group 6 don't form hydrides. Okay. It's confusing. Yeah. So these are like
Is Cr chromium?
Cr is chromium. Yes. So compared to ionic formed by S block, covalent or molecular formed by P block. So the third category, interstitial, is formed by D and F block elements. Not necessary that all of the elements form hydrides, all except group 7, 8, 9. And also in group 6, the smallest one, chromium, is the only one that forms the hydride. Elements below chromium don't form these hydrides. Okay. So interstitial hydrides are also called metallic hydrides. Metallic, self-explanatory, D and F block, all of them are metals only, so they are metallic hydrides. They are also called non-stoichiometric hydrides.
Metallic hydride, like the previous one was ionic hydrides. How is that different from metallic hydride?
So ionic, because S block ke saath, it's an outright ion, like you have Na plus H minus, or you have Mg2 plus H minus. In this case, it is slightly different. Metallic hydride, because also called non-stoichiometric, because in this case, ions are not explicitly formed. The hydrides take up spaces in the lattice of the metal itself. Like we'll elaborate on this. How are they different from metallic hydrides? We'll elaborate on this. We'll talk about the structure of these hydrides. And that's why they end up being non-stoichiometric also. These are like alternative names. The way ionic hydrides are also called saline hydrides. The way covalent hydrides are also called molecular hydrides. So interstitial hydrides are also called metallic hydrides or non-stoichiometric hydrides, alternate names. Okay. Let's discuss the more common properties first. These hydrides do conduct heat and electricity, just like metals, in solid state. But the conduction is not as much as the parent metal. So basically, if like copper is the best conductor, right? Copper and silver are really good conductors. But if you take copper hydride instead of copper, the conductivity decreases a little bit. Not insulating like plastics and rubber and all, they do conduct, just not as much as the pure metals.
Ma'am, I'm sorry, but could you like repeat what were non-stoichiometry like hydride?
I haven't talked so much about it yet, Rishabh. Like after this, we'll talk about non-stoichiometric.
Okay.
So these hydrides, again, like the name non-stoichiometric hydride comes from the fact that D block and F block hydrides are almost always non-stoichiometric. So stoichiometric का meaning है, just a moment, like I'll get back to this. Just finish noting it down and then I'll discuss what it means.
Ma'am, I still didn't understand the difference between these and ionic.
All right. What was that, Kaveri?
I still didn't understand the difference between interstitial and ionic.
Yeah. So that we'll talk about now. So stoichiometric means they are like the ratio of the components are small whole numbers. Like for example, if I take within hydrides itself, NaH, the ratio of both the components is 1:1, right? If I take MgH2, like it's all in accordance with law of chemical combination, law of constant proportions. This is always going to be 1:2. For every magnesium atom, you have 2 atoms of hydrogen. Non-stoichiometric का meaning है, it is not going to follow these ratios. So D and F block, what happens is when we say it is almost always non-stoichiometric. For example, if you consider titanium ka hydride ka formula, like based on the masses, if you were to reduce a formula, it's going to be something like TiH 1.5 to 1.8. So it's not in accordance with the valencies. It's not in accordance with the law of constant proportions. You can't do stoichiometric calculations with it. So that's the difference between ionic hydrides and interstitial hydrides. So D and F block ke saath, it's basically not dependent on the valencies as such. Other examples, lanthanum, like where lanthanides get their name from. So lanthanum ke hydride is of the form LaH 2.87. Ytterbium, symbol is YB. This is H2.55. So they are not whole numbers. This doesn't mean that hydrogen atom is getting cut or something. It's just that it's not a perfect ratio. It is not following the valencies. It's just take a random amount of the metal, put a random amount of hydrogen in it. So, and then when you end up calculating ki kitna percentage, like what is the composition of the metal, what is the composition of hydrogen, you don't get up small whole number ratios, you get decimals like this. Because it is not uniform, it's not in accordance with any rule as such. Okay?
Got it.
Other examples, vanadium hydride is VH 0.56. It's not even a 1:1 ratio. It's like less than that. So usually it's almost always non-stoichiometric. And based on this, you can see with deficiency in hydrogen. Like hydrogen is present in lesser quantities than what you'd expect. Like Ti usually shows oxidation state of +2. So TiH2 hona chahiye, but it's always less than 2. So lanthanum usually shows oxidation state of +3. So according to that, LaH3 hona chahiye, but it's less than 3, it's 2.87. So that's kind of how you figure this. So it's almost always non-stoichiometric with deficiency in hydrogen.
But H ka valency would remain same, right?
H ka valency is 1 only, no?
Then why instead of +3 it's becoming 2.
Like what I mean to say is that's what I just mentioned, right? So deficiency in hydrogen ka matlab, hydrogen is present in lesser quantity than what is expected of it. Like magnesium usually shows oxidation state of +2. Hydrogen ka valency hai 1. So इसलिए formula हो गया crisscross method से MgH2. This is perfectly stoichiometric. But for D block elements, Ti usually shows oxidation state of +2. Hydrogen hydride है तो -1. तो ideally stoichiometric है तो TiH2 होना चाहिए. But here that is not the case. It's ending up with TiH 1.5 or 1.7 or 1.8 that way. It is less than 2. So that's why we say deficiency in hydrogen. So similarly, lanthanum ka valency, like oxidation state, like the most common one it shows is +3. But according to that, La +3, H -1, LaH3 hona chahiye. But that's not the case. It's showing LaH 2.87. So that's what we mean by deficiency in hydrogen part. Non-stoichiometric, it's not a perfect ratio. Deficiency in hydrogen. Hydrogen is present in lesser quantities than expected. Okay. So once you are done noting this, next page I'll give some more examples, or you can like check it in your textbook. There's examples given in the textbook. Palladium PDH 0.6 to 0.8. 1:1 होना चाहिए, लेकिन it's less than that, 0.6. So the reason for non-stoichiometry, like why is it like this? I'll discuss in the next point. Okay, so let me know when you're done so that I'll flip the page. Okay, Kaveri and Ritu are done. Adit, Rishit, okay. Arnav, Smera and Sanat. Smera is also done, okay. Arnav done. Okay, awesome. So why, like with ionic, it seems pretty obvious. It is like straightforward ki theek hai, valency hai, and based on the charges, it gets equivalent. But D and F block ke case mein, why is that not the case? Like, why is it non-stoichiometric? So one theory is that people assumed that maybe the hydrogen atoms were settling in the interstitials of the metal lattice. There are a few words here. We'll take them up one by one. So earlier theory was that, like it was thought that maybe H, like the hydrogen atom, takes the interstices in the metal lattice. Okay, what does this mean? Let's unpack this now. Do you guys know what metal lattice is? Do you have an idea about it? Have you heard of this? Any of these words before? Interstices का मतलब क्या है? Metal lattice क्या होता है? Like any idea about these? Guys, yes, no?
I know lattice from like lattice energy. I know they mean separately, not together.
Okay. You have an idea of the words. Yeah. Adit, you were also saying something? Hello. Yes, please answer, because I need to know if if you guys are with me understanding what's going on.
Ma'am, I'm not aware of these terms.
Okay. Metal, like I'll tell you what metal lattice is. Okay. Do you know how metals exist? Like if I take a solid block of copper, let's say, and if I were to zoom into it, like copper, is made of copper atoms, right? So how are these copper atoms arranged? Like if you had to look at that part of it, what would you expect?
Right back.
Yeah, Sanat?
Like very less what is it? Intermolecular space, I guess.
Yeah. So less intermolecular space, matlab the atoms are arranged like close to each other, right? So they are rigid, arranged very close to each other in a specific pattern, or specific, like every atom has its own space and it occupies that. Lattice is a word that you guys had come across fairly. Do you remember what lattice is? Like, do you remember the context we talked about it?
We spoke in context of like lattice energy, where it was amount of energy required to break away like 1 mole of a substance.
That is lattice energy. What is a lattice? Is this three-dimensional arrangement of solids. The 3D arrangement of solids. So solids matlab wo ionic ho sakte hai, wo metallic, it can be metals, it can be ionic compounds. So many solids are there, right? Whenever you come across a solid, there's only two possibilities. Either it's a crystal, like the way you have ionic compounds and metals, or it is amorphous. So the way you have plastics and glass and things like that. The difference between crystalline solids, amorphous solids is that amorphous is random. Like you just put them very close to each other with minimal spaces between the atoms, wo to amorphous ho gaya. Lekin crystals, like ionic, like salts and all, they have a very specific 3D arrangement of the atoms. Okay. Very specific 3D arrangement, matlab, you guys must have seen fruits being sold, right? Can you imagine fruits being sold on like fruit shelves and all? Can you imagine how those fruits are stacked? Or if I gave you a random number of marbles or balls or something like that, some spheres, and if you had to like arrange them properly, there are many ways of doing it, right? Like either you can do it like this, where it forms like a proper square or a cube, or you can arrange them like a pyramid sort of a structure, where these spheres go in the gaps of other spheres. So that way, there's like many different ways of arranging spheres or atoms, and every, like, depending on the size of these atoms, different elements or different substances will choose like a different thing. So there's a whole logic behind it, which you're going to study in grade 12. There's a whole chapter about the lattice arrangement. But for now, just know that, there's like a very specific, like either this can be a arrangement, this can be an arrangement. That way, if we were to look at 3D structures, there are so many different types of arrangements. Okay. So within this, like if this was a lattice, there are gaps between the individual atoms, right? Like yahan pe ek gap hai. यहाँ पे एक गैप है, यहाँ पे एक गैप है, यहाँ पे एक गैप है. Like whenever you arrange balls or marbles or something, when you stack them up, it's not completely tightly packed. Even if you were to squish them to the maximum extent, beach mein there's going to be holes or voids that come up, right? So those spaces are called, like yahan pe you can see it's this shape, like a diamond shape ka gap. So these gaps are called interstitial sites or interstitials. Interstitial sites, or you can also call it interstitials. ठीक है? Chris, got the hang of it better? Like, are you understanding?
Yes, ma'am. Just 1 minute.
Okay, you're noting it down, yeah? So I'll show you guys a visual of it once you're done with this, okay?
Yes, ma'am. Done.
I'm just 1 minute.
Done.
Okay, I'm switching the screen. Let me know if you're still writing. Otherwise, I'll switch.
I'm just 1 minute.
Okay, I'll wait. What?
I'm just 1 minute. I'm just drawing the last the diagram and then it would be done.
Acha.
Okay, ma'am.
Okay. Yeah, this is like a brilliant image I found that explains it properly. So ignore BCC for now. Like BCC, FCC, HCP is something you'll learn later. But imagine the gray balls to be the metal atom ke sphere. So you see the gap between the gray blobs, like the gray spheres, may you have these small green ones and the purple ones. So you can see, so that's what earlier people theorized, that maybe the hydrogen atoms were being stuck in between the metal atoms, like in the interstitials, within the metal lattice. So this is how people thought hydrogen was occupying. So it's not exactly forming an ionic compound or a covalent compound. It's just stuck within the metal ka lattice work. So that is the reason they called it interstitial hydrides pehle. Yeah, so this is what it was thought. And if you were to look at the 2D spaces, you can see this is another example. This is like a 2D representation of the same thing. If the bigger like white spheres are the metal lattice, people thought beach mein the black dots are there, right? So maybe those were the these are the interstitial sites, the gap between the metal atoms. So maybe hydrogen was being stuck like this at random places. That's why it was not stoichiometric, and that's why the conducting properties were also there. Like that's what people theorized that it would be. Yeah.
Earlier, people thought in the D block elements wala hydrides, the H's occupying the spaces in the lattice.
Yeah.
And then after,
yeah,
how is that?
Yeah, like that's what people theorize that, and that is the reason they called it interstitial hydrides. That's where the name came from. Like it was non-stoichiometric one, non-stoichiometric hydrides because it was non-stoichiometric, but because this was the earlier theory, they called it interstitial hydrides. That's where that name came from.
Then, like after the how was the theory proven wrong?
So what happened is, again, when people started studying the structures, like actually experimentally seeing the structures of it, they found that it was disproved by the fact that the lattice structure of the hydride. So how was it disproved? Lattice structure of the hydride was different from the lattice structure of the parent metal. Is different from the metal lattice. इसका मतलब क्या है? So if this theory was correct, it should mean that metal lattice structure जो है, within the gaps, in the gaps within that metal lattice, hydrogen is occupying the spaces. मतलब the original lattice is not disturbed, but experimentally it's found that hydride का lattice जो है, that structure is different from the parent metal का original lattice. So I told you there's different types of arrangements, right? Like you have they're called unit cell, they're called Bravis lattices. So there's like 14, I think, 14 different types of structures. You have CCP, you have HCP, you have BCC, edge-centered cube, all of that stuff. So the lattice structure that the hydride was taking was found to be different from the metal lattice itself. So that disproved the fact that hydrogen was just occupying spaces. The exception, like it was different from metal lattice mostly, but for nickel, palladium, cerium, and actinium, it was the same. So these are like the exceptions to this. In these cases, the hydride ka lattice was the same as a metal ka lattice, but majority of the cases, all the other D block hydrides ke case mein, the lattice structure was different. So that's how the
means in palladium and all that the hydrogen is actually in between the lattice.
Maybe like it was just found out that this particular lattice structure is the same, but like research is still ongoing. I don't exactly know whether that interstices mein hi hai ya fir is it a completely different structure, like those details we don't know.
So I didn't get it. Like the lattice structure of hydride is different from metal lattice. So what exactly?
It means that agar lattice structure hi alag ho raha hai, if the structure itself is being rearranged, then it means that hydrogen is not just occupying the gaps. It is actively a part of the lattice structure itself. It is disturbing the lattice structure itself. So there is some sort of a chemical thing going on there.
Okay, got it.
Okay. So another speciality about D block hydrides, like specifically some of them, so they are capable of absorbing hydrogen. So absorbing is it's a process. Like absorption, like a sponge absorbs water. It takes it in within this whole body of the sponge itself. Adsorption is a process where the thing that is being adsorbed, like the substance is deposited on the surface of the material. Okay, so it's a surface phenomenon. So D block metals are capable of adsorbing hydrogen. So this adsorption of H is used, like, because D block metals, especially metals like nickel, palladium, platinum, so these kind of metals are very good for adsorbing hydrogen. Adsorption matlab, if this is the metal block, it basically, and if you have hydrogen gas here, like double bonded diatomic hydrogen gas, so this bond breaks and each of these nickel atoms forms a bond with the hydrogen atom. So basically you find hydrogen atoms deposited on the surface of the metal. So that process is adsorption. It's just stuck on the surface itself. And on heating, the hydrogen will be, like, you can release this hydrogen from the metal just by heating this metal block. It's a physical process. Physical matlab, like you have physical adsorption, you have chemical adsorption also. Like if this bond breaks, it's a chemical process, but it's not a chemical reaction as such. You're not forming like a completely new substance. You're breaking this bond, putting the metal over, like putting the atom over the metal, and that's it. You're not forming like new this thing as such. So this adsorption of H, like you make use of this particular property or the process in catalytic reduction and hydrogenation reactions. You can use these metals as catalysts for any reaction involving hydrogen. Catalytic.
So in ones where hydrogen is not actively part of the lattice, it is on the surface.
Yeah. Yeah. Adsorption matlab, it's like stuck on the surface.
So it's either, so there are only two options: either it's actively taking part in the lattice formation, or it's on the surface.
Not necessarily. Like these two cases are observed. Like in this case, I'm mentioning that because it's on the surface, this adsorption, we take advantage of it by using it in reduction reactions.
Ma'am, your voice is cracking for me. Could you please repeat that?
Huh. It's not black and white, like it's not just this or that. I'm saying, like in the cases, like this is a completely different point. So in the cases where hydrogen is being adsorbed, like by metals like nickel, palladium, platinum, so where it is being just deposited on the surface, we make use of that property by using them in these reactions, in hydrogenation reactions. Like these metals
So
act as a catalyst for that.
As a catalyst means what? They're already like reacted with the hydrogen, right?
Like that's why they are the catalyst. So catalyst का काम क्या है? It speeds up the reaction. So अगर ये use नहीं किया, then you need to provide energy in breaking the bond. But by using nickel, you don't have to use this like you don't have to provide this energy anymore. It's automatically breaking the bond because hydrogen atoms are bonding with these metal atoms, like being on the surface of this metal. Like that's what adsorption is. So you save this energy and then directly you can use this hydrogen in the reactions.
So means for catalytic reactions and all that, like to obtain hydrogen gas, instead of like giving that all that energy, you could just make it into a hydride and then heat it up and then it'll be released.
Correct. Yeah. Yeah. Essentially, you're using these metals as a catalyst. And how are they acting as catalyst is by adsorbing hydrogen, adsorption of hydrogen, making use of this word.
This is still forming, like the nickel, palladium, all that is still forming a hydride with hydrogen, right?
Yeah.
Could you go back a slide?
This one, right?
Just 1 second. Okay, ma'am.
Yeah. So that's it about interstitial hydrides. So basically, D block elements, they absorb hydrogen or they absorb hydrogen, and you can basically like use them as storage for hydrogen. Like that's what research is looking into now. Like, can we use these metals? Again, it poses a problem because metals like platinum are pretty expensive, right? So that's another separate branch of research that's like ongoing. But that's an option that people are looking into. Okay. It's 5:27 already. So, oh, I thought we could finish it today. Didn't. So we just left with water. Like water ke 4 reactions are there, and there's heavy water. Heavy water is also tiny, which is different from water. So it should take another hour, maybe. Shouldn't take more than 1.5 hours. So let's complete this next session.
Will we start hydrocarbons after this?
Yeah, we can start. Either we can continue, like we can do questions of this chapter, or immediately after this chapter, we can start hydrocarbons. Either way.